holography to recursive proofs, and more importantly, what each of these things are. The material for this talk is based on 2 recent papers with several great colleagues. Some of them are here. Nick, there is also Mary somewhere. Insong is here, maybe. Oh, hi, Insong. And Dev, not here. Okay, but okay. So these are references. They're online if you want to read about them. So at high level, what I want to discuss today is a new methodology for recursive SNARKs. I will explain what recursive SNARKs are. I should also clarify that the emphasis of today's talk is specifically on, let's call it concrete efficiency. So in the sense that SNARKs are being proofs of knowledge and succinct. We know that they recurse, but we want to recurse them in practice with actual implementations. And in these recent works, we discovered a very interesting connection between an information-theoretic concept, something called the holographic proofs, that is strongly connected to efficient recursion of SNARKs through the notion of preprocessing SNARK. Okay, so that's kind of the way the structure goes. And I will have 2 actually rather quick parts for the talk. We only have half an hour. First, I will explain you why recursion of SNARKs is particularly efficient when you start from a so-called preprocessing SNARK. And second of all, I will explain why this information-theoretic notion of holographic proofs directly leads to preprocessing SNARKs. Okay, that's the plan. So let's start with the first part. Actually, why should one care? This methodology, we have found it to be quite general in the sense that it leads to recursive SNARKs of very different types. 2 quite different examples is that you can sort of apply this methodology to obtain quite efficient pairing-based recursive SNARKs based on a so-called universal setup, universal structured reference string. That's what SRS stands for. Or alternatively, something quite different would be post-quantum and transparent recursive SNARKs. Now you're only using kind of random oracles and hash functions. And here transparent means that you're only using, again, so no trapdoors. Okay, so part 1. Why is recursive composition and preprocessing related? So first, let me remind you what is recursive composition. A motivating example is, for instance, say that you want to prove the iterated application of a given function f. Okay, you want to do it one application of f at a time. So you have some proving procedure that depends on f that produces a first proof for the statement. Let's say that f applied on some input 0 gives you the output z1, right? And in a second step, you would have the proving procedure actually build on the prior proof and produce a new proof for the statement that f applied twice from 0 gives you z2. Okay? But you don't want to start from the beginning. You want to leverage the fact that you already proved the first step. Okay? You want to prove incrementally many times until some number of times t. This is, say, the tth application of f on 0. And you want it to be so that at any moment in time, including at this point, you can check quickly the correctness of this, say, computation. Okay? Yes?
Is it crucial that every round always, so here every round that you never get a new input, right? So is that crucial?
No, I was just simplifying. In fact, it is useful and interesting the fact that you can provide different inputs at different iterations. Here it was just a particular example. Now, you can formalize this through something called incrementally verifiable computation. This is what guys spoke about yesterday. And more generally, something called proof carrying data that generalizes this notion not just on line graphs, but any directed acyclic graphs. And there are applications of these notions. You can, for example, construct delegation SNARKs for MapReduce computations. You can actually build something called verifiable delay functions. This is actually the actual construction. You will get a verifiable delay function if you do this. You can build succinct blockchains. Isaac is here and has co-founded a company precisely in this direction. And also you can prove PPAD hardness, as I actually learned yesterday. I hope I got the references right. Now, in all of these settings, the reason why doing these proofs of proofs is even make sense is because you have some form of fast verification, okay? That the NP statement that this procedure is called upon to check is, of course, the invocation of f on the prior input plus checking the prior proof. And you want this prior proof to be faster, checking that proof to be faster than the statement it was attesting to. Otherwise, you're just accumulating more and more gates to prove, and there's no point to do it incrementally. Now, let's try to kind of look under the hood and see specifically what costs arise when you try to kind of you prove things recursively, okay? And in particular, we need to clarify what do we mean by fast verification. So now I'm going to make that precise, okay? So you could say, well, let's consider machine computations. I'll just informally call this relation MSAT. Also, let me point to the fact that today I'm going to be using relations that are actually triples, not pairs. Why I want to specifically separate kind of the description of my computation, M, the machine, from its input that says, I want to run M on X for so many steps. Okay, and this is the witness. So I'm going to look at relations that are actually triples. Okay. If, for example, I'm focusing on machine computations, fast verification will say that I am able to produce a proof such that my verification procedure is polynomially related to the description of the machine and the input. So let's make sure that this makes sense. If I read the machine, obviously I will read maybe the finite automaton that represents the Turing machine, or you can think about it as the program, the input to the program, and the time bound in binary. So that costs me log t. This is compared to the complexity of the running the computation. It's m times t. Okay? So this could be much, much larger than representing kind of the statement itself that I'm checking. So a SNARG for machine computations would achieve succinct verification if you're able to check proofs, let's say, polynomially in this expression. When I say polynomially, I'm folding into it security parameter and so on and so forth, right? Fine. This is what fast verification means. By the way, we do know that there is theoretical work that says whenever you have a snarg of knowledge, say of this sort, then you can do recursive composition. But today I'm going to talk about preprocessing because I want to motivate that. So I'm also going to bring in, as a comparison, circuit computations, okay, where now the machine is replaced by an explicitly written circuit. Okay? Again, it's a triple. You have the circuit, the input to the circuit, a partial input to the circuit, and the rest. Okay? And of course, the representation of the statement that I'm checking, which is C and X, is roughly the size of C, right? So in this case, you would think, OK, I might be able to get a short proof, but certainly I will not be able to get fast verification because guess what? I have to read the circuit. OK? However, there is a setting of SNARKs that is called preprocessing SNARKs that let you achieve fast verification. How? You have some offline procedure that is done once and for all for a particular circuit that generates a so-called verification key that is specialized to the circuit at hand. Okay? Think about it, as a mental picture. You hash the circuit and you keep its hash in your pocket. Okay? And then you can check, and anybody can do this. Okay? There's no maybe trapdoor associated to that. And then every time you check a proof relative to that, you will pay, say, log in C. Okay? All I want you to take away from this slide is that we have two incomparable settings for fast verification. One is we're going to achieve fast verification for some computations without preprocessing. Which some? Where the ones where the description of the computation is much smaller than the computation itself. And the other setting is that we can achieve fast verification for all computations, say arbitrary circuits, but we're going to have preprocessing. Okay? These are formally incomparable. Okay? Now, theoretical work in recursive SNARKs tends to focus on sort of this maybe cleaner, simpler sort of formulation of fast verification. I want to now tell you about why this setting here is particularly suitable for recursion. Yes?
It's going to be non-adaptive, right? But in the machine setting, it can be adaptive?
Excuse me, could you please repeat the?
In the circuit setting, it has to be non-adaptive, this preprocessing.
What does not? So you're saying who does this, or?
Or like you. So like I'm saying, like in the machine setting, you can have a scheme that's adaptive. Or
In.
so like the computation can be chosen.
But the adversary, saying first you choose a CRS and then the adversary chooses the
Yeah.
computation.
So I'm not gonna discuss security definitions, but I am. Let's say that by default, I'm assuming full adaptivity in all relevant parameters. For
Enough that you kind of bake adaptivity.
not just that, but if we use it for recursion, you need sufficient adaptivity in your soundness, and not just soundness, you need sufficiently adaptive proof of knowledge because you need to extract. But for example, just a second, Omer. For example, it is okay for the adversary to choose which, say, X to prove things about as a function of the verification key itself. Okay. Similarly here, it would be okay to choose even M, X, and T as a function of whatever parameters the SNARK, every SNARK will have some setup, and it's okay to pick them adaptively. And this is important for recursion. Omer, you had a question.
So the preprocessing step doesn't have any secrets, right? I mean, can it be deterministic, or?
It better be deterministic, or at least you can. It could be probabilistic, but then you would have to publish the randomness for others to reproduce. And then, there are other separate issues that I don't want to discuss right now that are not about that. Clearly, if it is as private coin, you have certain things that might go wrong, but even if it's public, though I am assuming adaptivity throughout the talk, and I'm not going to talk about it further unless you force me to. Okay. So now I want to explain, this is probably the only difficult slide in the entire talk, okay, like really. I want to explain why preprocessing helps in recursion. For that, I have to show you how you actually go about and prove things recursively. So here's the machine. I'm describing a machine, R, for recursion, that will implement this incremental application of F that I had as an example at the beginning of the slide, beginning of the talk. So it takes two inputs, the input X and the witness W. The input X, it will parse it as a description of some arbitrary machine. For now, it's not the same one. Just some arbitrary machine, the counter where we are, and the current claimed output. The witness will contain the previously claimed output and a prior proof. It will check the transition is applied correctly, and if you're not in the base case, it will check the prior proof. Now, check the prior proof, you have to specify which NP statement we're going to be checking against. So it specifies this prior instance with the counter one less with the prior output, and it specifies that it's going to be relative to the machine M, which is an input to the computation. All right? So later, what you do is you set M to be the machine R. Okay? So it will actually, R will be called upon checking a computation that involves itself on an input. Okay? I could have also invoked the recursion theorem, but probably nobody has it loaded in their head, and I just kind of did like a poor man's version of the recursion theorem using the environment here, okay? So, right? But the point is that now you prove that the machine R accepts on input xi where I've replaced the description of M with the description of R, specifically R, okay? So there's nothing that is circularly defined, I really can roll it, okay? And you would run verify on this, okay? Okay, that's easy. I could do literally the same thing, or almost the same thing, in the circuit world. Except that now I don't put the description of a circuit here because it doesn't make sense. The circuit, I don't want the circuit to read descriptions of circuits. Really what it should receive is verification keys. Okay, so you see I've replaced this by verification keys. Okay? And similarly, when I'm proving, I will pass in as an input to the circuit R its own verification key. Okay? Generated based on R. Okay, so what? This is just a syntactic change, but here's the punchline. Let's look at what is the cost of the recursion, let's say as a function of F. What I would like is that the cost of proving things about F is as close to F as possible. I don't want my cost in F to blow up. So here, if you notice, I am going to pay for a cost in F that is pretty steep. Why? Where does F live? F is hard-coded in the description of R. And R is passed as an input to R itself. So it means that the machine R is called upon to interpret the description of f and check it. This will cost you some number of logical steps just to figure out where is r, where is f, what does it look like, let me kind of execute it and see if it's running, okay? So we'll pay at least some multiplicative cost, and it's going to be like highly non-trivial constant here, plus other stuff, including the verifier and everything. But at least you have a cost here. In preprocessing, it's not going to happen. You are just considering a circuit, and I'm going to take f and I place it in a particular place in the circuit. There is no parsing, no interpretation. You can think about this as the difference between some hardware recursion and some software recursion.
Sorry, what is capital F? Capital non-italicized F?
Capital, I'm sorry, this f should be this f. I know they're completely different symbols, but this f here and that f should be the same.
So F is also the original machine or something? Or
what I'm trying to measure is I have a predicate or a function that I want to recursively apply at each step. And I want to measure the cost of my recursion as a function of that predicate.
So the size of F means like the description of the machine?
Let's take of f as a circuit in both cases. And if it's a machine, then I will have to write here time of f. Right? Yes, f is the thing I was iterating.
Number of gates, right?
You can think, yeah, the size of f is, let's say it's a circuit, and it's the number of gates. The point being is that in hardware recursion, I pay 1, okay? That's it. And what has happened is that preprocessing has replaced the description of R with a succinct cryptographic commitment to it, okay? And this is something that will always happen with the preprocessing SNARK, okay?
Sorry, why is the time R, why is it C times?
Because F, let's think about it as a circuit, it is hard-coded in the machine R, right. And the machine R is called to run on an input that involves R as it's the description of R, and it has to check F. So it has to kind of decode or parse F somewhere in its input and run it. So it receives the description of a circuit and has to check that it's satisfied.
It could be F plus also C, isn't it? Like just.
I really have no idea how to do that. Like for concrete, I mean, maybe. Oh, okay. I'm just saying that for a preprocessing SNARK, I can do it. I can actually prove it for every preprocessing SNARK. This is the case. Like this is for natural constructions of. I really don't. And this constant, like I've thought with my colleagues quite a while about this constant. They're just really not nice. Okay. And it's a nice open problem to see whether there exists something on the left, or you could have something like c equals 1. But on the right, you definitely have it c equals 1, because you're doing hardware recursion. Good. This is the only difficult slide of the talk. And you can prove things that any preprocessing SNARK recurses, and you always have under some very mild conditions, you always have this kind of non-multiplicative cost in recursion. So this is something that we analyzed in a recent work. I should also point out that recursion preserves your knowledge. It also preserves important properties such as post-quantum security. We didn't know that before. Now we know that if you start with a post-quantum SNARK, you can recurse. You'll get a post-quantum, say, incrementally verifiable computation and proof carrying data. And maybe another small remark is that recursion preserves the type of setup. So if you have a preprocessing SNARK that actually does have a private coin setup that depends on the circuit, you will get a circuit-specific recursion. And this is actually what is deployed today. We know it's constructed from linear interactive proofs and pairings. And in hindsight, the reason why we were able to have efficient realizations of recursion is because we based it on preprocessing SNARKs. Now we see today why it was much more practical than alternatives. Okay, there's it's a common explanation for all preprocessing SNARKs. The role of so-called pairing-friendly cycles of elliptic curves to make this practical is really just to make this smaller, but it doesn't the statement that preprocessing helps is just true regardless. Okay. So where does holography come in? It has to do with this other very interesting setting. Like this today, we are very interested in setups that are universal. You set it up, say for all circuits up to a certain size, or you just have public coin setup. And we don't really have a very good explanation of where preprocessing SNARKs in these other settings come from. And what I'm going to explain in, I think, 5 minutes suffice, is that it comes from holographic proofs, okay? So the lesson so far is that if you're interested in recursive composition, especially efficient one, you should care about preprocessing SNARKs. If you care about preprocessing SNARKs, then there are different types of preprocessing SNARKs as a function of which setup you're considering. And the practically interesting setups typically are the ones that are universal or transparent. Then you would like to have a methodology to construct preprocessing SNARKs in those settings. Okay? And there is a very direct connection from holography to this setting, yes? Yeah, just I put in parentheses here, uniform reference string. That's just a reference string that is fully random. A question? All right, and it basically handles these cases. So all I really want is to explain what is holography, and there's like extremely simple compiler that tells you how to go from holography to preprocessing. So let me take as a running example again CSAT, and I'm going to talk about PCPs. But the concepts that I discuss really apply interactive proofs, interactive PCPs, interactive oracle proofs. They're kind of orthogonal, like to the specific type of proof that you have. You can also apply them to NP. So standard proofs, you have the traditional notion of completeness and soundness that says that if you're in the relation, then the honest prover will give you a proof that makes the verifier accept. And if you're not, okay, if there's no witness that makes C accept input X, then you reject with you accept it at most with some probability regardless of the proof. Now, in the setting of arbitrary computations, we don't want to touch C. C is too big. Okay? We have to take it out of the verifier and put it somewhere. Okay? Now, there are two classical answers to doing this. One is proximity proofs. Okay? You just say, yeah, you have oracle access to C. Okay? Now, to actually make it possible for the verifier to touch C at a small number of locations, you actually have to relax your decision question. You're really going to consider this kind of proximity version of soundness that you're not going to check this condition. Instead, you're going to check, let's say, that C, if C is delta far from all C star that make X be satisfied, that make X a good input, then you're going to reject. Okay? I don't really know how to weaponize this for our SNARKs. I mean, it's a fine notion, and we use it as a tool to construct many useful things. But there's an orthogonal relaxation that you can do, which is holographic proofs. You're going to say, OK, we take out C from the verifier, but now it's going to be kind of encoded in some form. There is some algorithm. We call it the indexer, because I'm thinking of C as kind of the index of a relation R sub C, that takes C and spits out some string based on C. OK? And now you get to keep your original promise, except that now the verifier has access to this processed input. OK?
And that's guaranteed to be.
Yeah, like it's yes, it's here. Like that's what it is, and that's what you have access to. So that's a sort of general notion of holographic proofs. Any questions about this one? Yeah, it's simple, right? So it's a simple, clean notion. It's orthogonal to proximity proofs. And now.
How big is this I of C?
It depends on how good is your proof system. Similarly, just how big is pi as a function of C. You know, all of these are parameters of the proof system. If you build holographic proofs, you better care about the size of I of C. That would be one additional measure of complexity that you want to keep under control. Because if you don't, then you'll pay for it. So in these two papers, we actually explored this connection from holography to preprocessing in two different settings. One is this information-theoretic compiler that we proved that any holographic PCP, or more generally interactive oracle proof, leads to a preprocessing SNARK in the quantum random oracle model. Okay, so this is really an information-theoretic statement. There is nothing but random oracles, and actually a very simple compiler. I'll give you, it takes like 1 minute to explain. Another is a cryptographic compiler that says, let's consider something called an algebraic holographic proof. Essentially, it's the same thing, but you talk about polynomials instead of strings. And you can compile it into a preprocessing SNARK in the square RS model. What is square? Well, it's either SRS or URS, depending upon how good is your extractable polynomial commitment scheme. Okay, so you have some polynomial commitment scheme in some model, you inherit it here. Meaning these are two very different settings, information-theoretic and cryptographic, where kind of distilling the notion of holography and just being honest to yourself that that's actually what you're talking about all along makes it very easy to see where preprocessing comes from. By the way, when you take the random oracle and instantiate it heuristically, you will get something in the URS model.
So can I ask you something?
Please.
The addition of Q. What is it? I mean, what is the? Can you say something about the proof being more complicated than if it was just without Q?
No, this is just saying that this is like a classical construction in the random oracle model that, in addition to being information-theoretic secure against classical adversaries with bounded access to the oracle, it is, moreover, secure against quantum adversaries that make bounded number of queries to the oracle. So this is a statement about post-quantum security. Yes, up here, this is about the information-theoretic compiler in the random oracle model. There's nothing but random oracles. Yeah.
In order to make it secure against quantum as well, it's not just increasing an assumption. There's no assumptions.
There's no assumptions.
What is it?
So the statement is something like this. You have a unbounded quantum algorithm that has superposition access to the random oracle. This is the standard setting of the quantum random oracle model. I didn't make it up. It's a paper. Yeah. But the limit of the quantum algorithm is the number of queries to the oracle, but they can be in superposition. Number of superposition queries, right? And you want to relate the soundness error of a compiled protocol to this bound, okay? And the kinds of statements you probably want to prove is something like this. If your PCP has, say, a soundness error epsilon, which is, it's not about quantum, it's about the PCP, out here, you will get, say, a soundness error that is maybe t times epsilon plus something small against t-bounded quantum adversaries.
Andrew's analysis of the BRF of the Silverman functions?
I'm not aware of connections. It is.
That he also gets a superposition of.
Nick, are you aware?
So this uses his compressed oracle formalism. So this is the indifferentiability. The argument that like sponge constructions are indifferentiable from the random oracle. This uses this argument. PRF thing, I don't know.
Maybe we can explain it offline. I mean, there is many things happening here. But, all I want for now, let me just say that the statement, the Q here, just saying this construction is post-quantum secure, information theoretically against.
Is there some connection between the second line here and the SETI Spartan work? It feels like you could imagine generalizing into a compiler from multi-proof or interactive proofs with sort of indexer of C, which is...
I believe that if you work hard enough, it would be a special case. By hard enough, I mean that it actually matters which properties of the polynomial commitment scheme kind of make this transition go through. All right, so I want to conclude with my last slide, which is actually I want to tell you the information-theoretic compiler is very simple. It's kind of so simple that it's kind of weird that we think about it only now. So step A, we just apply the Micheli transformation, and we leave the indexer as is. So you have your PCP, you apply the Micheli transformation, and you will get some sort of holographic snark, right? That somehow, because the Micheli transformation never really touched the PCP verifier, if before the PCP verifier was happy talking to an encoded circuit, then he continues to be happy talking to an encoded circuit because there's anyways a tiny PCP verifier here talking with the outside world. So this I'm really I'm applying the Micheli transformation as a black box. And then it's kind of clear what you should do. It says, look, you wanna answer queries about this string I of C. Just in an offline stage, just take your circuit, encode it, store your root in a verification key, put the rest for the prover, and during the actual proving, figure out which queries the verifier wants to make, package them up in a proof, send it along, and run the Micheli verifier answering, like this. And that's it. Okay? So in the information-theoretic compiler is just basically the observation that if you have an extra kind of offline kind of PCP that is just about the circuit, it's not about computation, then you can just push it into a Merkle tree once and for all. Okay?
Is also secure in the quantum random oracle?
Yes. It's a good question, and this is one of the things one can prove. Yeah, and in fact, here you don't even need to use the analysis of Micali in the random oracle model. You can just use actually the way we prove this is by just using the collision bound.
Natural construction that are secure in the random oracle model, but are insecure in the quantum random oracle model.
There are separations, but I don't know if there are natural ones. Okay, let me just conclude and say that we have holographic proofs. In fact, we have classical holographic proofs. BFLS is one of them. That already gives you very interesting results in preprocessing. We did not know of preprocessing SNARKs that are post-quantum. Now we do, just even by applying BFLS. The bare bones GKR protocol is also a holographic proof. And what Nick talked about earlier today basically gives rise to, eventually, holographic proofs with reasonable parameters, including the indexer. So this goes back to your question, that the encoding size will be linear in the circuit, and you can obtain it with an FFT. Okay. I think I'm gonna conclude here. I'm gonna go to the final slide. I have some graphs, but I think you can ask me offline. So what I told you today is a new methodology for recursive SNARKs. I explained why, if you care about recursion, the efficiency of recursion, you should care about preprocessing SNARKs. And then if that's your new target, then a good way to reach it is by designing good holographic proofs. Thank you. Okay, yes, please. Of course. Yeah, I know. Sorry. So, sure. Let me go through this. So I put here 2 preprocessing SNARKs that are generated using holographic proofs. These are 2 recent papers. And I am plotting for each of these 2 things the closest representative benchmark. So for example, this one is a preprocessing SNARK in the universal SRS model. And I'm comparing it against the best circuit-specific preprocessing SNARK. Circuit-specific, meaning preprocessing is is based on the circuit. The other benchmark here is I'm comparing a preprocessing SNARK in the quantum random oracle model, instantiated heuristically using hash functions, and I'm comparing it against the best non-preprocessing post-quantum SNARK. And I think these are actually very interesting graphs. And there's some, I think, high-level takeaways for everybody. One is that prover time basically doesn't matter. Like, all of these systems are within a factor of 10 of one another. You might think, oh, a factor of 10 is a lot. But in the grand scheme of things, these are using very different tools, different instantiations, and the fact that all provers are within a factor of 10, and all of this is, again, for rank 1 constrained systems, okay, is, to me, interesting. Like, it's saying, like, all the provers are, to a first approximation, kind of doing the same thing, encoding FFTs and doing some interesting stuff underneath. Another interesting takeaway is also the verifiers, that for all preprocessing SNARKs, all verifiers are pretty fast. We're talking about from 2 to 10 milliseconds. Again, they're all pretty good. What's this line? Well, it's the only non-preprocessing SNARK here where the verification time grows linearly. Well, of course, it goes up. But this is basically saying that, to me, verification time is not really like a separation between these approaches. Performance-wise, what distinguishes a lot between these is the proof size. Circuit-specific preprocessing SNARKs give you ridiculously small proofs, less than 200 bytes. If you go universal, you'll get less than 1.5 kilobyte. Okay? Why are they writing here instead of in the graph? Because this is 10 to the 4th byte. Okay? So they would be like down here, and you wouldn't be able to see the difference between these. Here, it's basically saying that the cost of preprocessing relative to non-preprocessing is within a factor of 2. Okay? So the difference between all these schemes really boils down to proof sizes, and then of course the different setups and whether they're post-quantum or not. There was a question back there.
I'll ask you offline.
Okay. So then some empathy for the rest of the audience. So I think we should take a break. Yeah.